Language model memory is a new AI feature that big tech is happy to give us all for free. Like anything big tech gives us for free, it is because we are the product. Rather than getting further reliant on handing over all of our data to big tech so we can benefit from AI, in this video, we will build a local Ollama RAG agent that stores every conversation in a vector database on your PC. The program we will be building today has local data storage, local embeddings, and local open source language model inference through the Ollama open source interface, which means this AI gives you 100% data privacy and security when prompting your memory-enabled assistant. This agent uses a first principle retrieval augmented generation technique to handle pulling context from multiple needles in the haystack. In other words, this AI creates queries to search for data on multiple topics to satisfy the needs for responding properly to your prompt. After retrieval of the most relevant embeddings on various topics from our conversations database, the agent then runs a prompt on each retrieved embedding to classify whether it is useful context for responding to our prompts. Once each embedding has been classified by an LLM, then our prompt is constructed with only the relevant text chunks in our prompt. Thanks to Ollama, we can run dozens of open source language models in a model format that is already quantized, meaning optimized to run locally on consumer PCs with maximum efficiency. That means whether your PC is begging for retirement and you need to run a smaller language model, or you have a custom AI GPU box for inferencing 70 billion parameter models, this agent can be built to run efficiently without ever sending data out to a cloud server. Like most of my videos, this will be an in-depth code tutorial. If you do not have the patience to go through a video tutorial and just want my source code for the program, it is available in the Pro channels on my Discord server. In the Pro channels, you not only get the source code for all of my video tutorials, you also get access to written Pro tutorials 1 to 2 weeks before the videos go live on my YouTube channel. As just one mortal man, these videos take a ton of time to create with the amount of editing needed to make an engaging programming tutorial, whereas a written tutorial takes me far less time to create for people that want the earliest access to my code tutorials and all of my source code. If you do want access to my source code with full rights to use however you please and early access to my written tutorials, click the Buy Me a Coffee link in this video's description. To build this program, you will need to have Python 3.11 or 3.12 installed correctly on your PC. We'll also need to install Ollama from their official site. Once those two installations are complete, we can create a folder to store all of our program's code. Then open your new folder inside of VS Code or whichever code editor that you prefer. Next, we can install the Python libraries we will be using to build our RAG agent. Create a file called requirements.txt, then copy all of the text the same as mine and save this requirements file. Open a new terminal for Mac and Linux users or command prompt as admin for Windows. Now run this command to install all of the Python libraries in requirements.txt. After hitting enter, watch your terminal output during this step and make sure you don't get any error messages while installing the Python dependencies. Before we start writing some code, you should test which Ollama models are going to perform the best on your PC. My recommendations are the Llama 3 and Mixtral models. If your PC cannot handle these bigger models, my recommendation for a mini language model would be Phi 3. While a language model like Llama 3 8B is going to give you far more intelligence than a 3 billion parameter language model, out of the 3 billion parameter models I have tested, Phi 3 is giving me the most fire performance. Now we can create a file called assistant.py. The first step we will want to accomplish with this program is getting it to prompt the language model through the local Ollama API and print the AI generated response. Start by importing Ollama, then create a variable named output that will store the response from calling the Ollama API's generate function, specifying your model of choice and writing your prompt inside a string variable for input parameters to the function call. Inside of the response variable, we will select only the response value from the output and finally print the response. Save this file and you should now have a Python program capable of inferencing a language model 100% locally. Something to note when using Ollama to power your Python scripts is you need to start up the API before running your Python scripts. You can do this by running any Ollama model and allowing the chat app to start before typing the buy command. Next, we want to make our program fully conversational, so we can delete this current code and create a variable called convo that will start as an empty list. Create a while true loop to infinitely loop through our next 6 lines of code. We can request an input from the user to be stored in prompt. We can then append the prompt formatted correctly for the Ollama chat function to our convo list. Inside of output, we will call Ollama's chat function instead of the generate function we previously used in our code. Again, specifying the model, and instead of passing a prompt string as input, we will pass the convo variable to the messages parameter, giving our entire conversation as input to our chat function. Inside response, select output's message content value. And now we can print the response from our assistant and append the formatted response to our convo list. By running this program, we can now have conversations with our LLM that will remember all of the context up to the model's limit. Ollama will automatically handle context overflow and trim the earliest messages in our conversation to prevent any error messages from passing too much context to the language model as input. Now, instead of having the program wait until the full response is generated to print, let's implement Ollama's streaming response capability to dramatically reduce latency from our assistant. For this, we will define a function called stream_response that takes prompt as an input parameter. On the first line in the function, we can copy in our line from the while true loop to append the prompt to combo. Our response variable will start as an empty string. Inside a variable called stream, we will copy in the function called to Ollama chat and add stream equals true as an input parameter. Before printing the streamed response, we can print the assistant message header. We can use a for loop to check for chunk in stream and select the message content value to store inside a variable called content. We can add the content to response and print the content, specifying the end to equal an empty string and flush equaling true. Once the for loop has completed, our response is done generating, so we can print a line break to keep our terminal clean and append the formatted response to convo. Once our stream response function is complete, we can go down to the while true loop and delete all but the first line and call the stream response function, sending the prompt parameter to equal prompt. With a Python program capable of conversationally streaming language model generated responses locally, we now need to be able to create vector embeddings of our previous conversations. For those of you unfamiliar with what vector embeddings are numerical representations of text or even visual data created using advanced machine learning algorithms to represent the meaning of a piece of data with numbers. After the meaning of all of our previous chats have been converted to number representations, when we send a prompt to our assistant, the prompt can be converted to a vector embedding as well. Using the power of math, we can calculate which of our previous messages are most similar to our current prompt. That's the concept of vector embeddings in regards to large language models. Now let's create them in our code. Start by running this command to download the Ollama Nomic embed text embedding model. Ollama does have a few other open source embedding models you can try, but Nomic has given me the best results. Inside of our code, import ChromaDB, which is the vector database that we will be using to store all of our embeddings that Ollama will be creating. Inside of a variable named client, initiate ChromaDB's client class to start up the database on your PC. Inside of a variable named message history, create a list to store 3 sample prompt responses, each in a dictionary with an ID variable. Define a new function called createVectorDB that takes conversations as an input parameter. In the new function, create a variable named VectorDBName as conversations. Now we want the program to delete the conversations database if it already exists, so that it doesn't add copies of our message history every time we run the program. Use a try statement to call client's delete collection function with name equaling VectorDBName. If the collection did not already exist, an error message will be thrown, which will be handled by this try statement by calling pass for any value error exceptions. Inside VectorDB, call client's create collection, again passing name equals VectorDB name. The conversations input variable for this function will be a list of conversations just like our message history variable. So we will loop through each conversation in the conversations list by writing for C in conversations. Inside of the loop, we will create a variable named serializeConvo that will format the text for the vector embedding. Inside of response, call the Ollama embeddings function specifying Nomic embed text as the model and prompt to equal serializeConvo. Inside embedding, store the embedding value from response. Now we can call the add function on our conversations vector database to pass the IDs equaling ID of that message, setting the embeddings parameter to be the embedding inside of a list and documents to equal serializeConvo inside of a list. With that done, above the while true loop in our code, we can call the create VectorDB function passing the message history as our single input parameter. Our program now creates a vector database of all of our message history added to the list. Let's now get the program to create a vector embedding representation of each prompt input and mathematically retrieve the most relevant embedding from our database. Now define a function called retrieve embeddings which takes prompt as input. We'll first convert our prompt to a vector embedding. Inside response, call Ollama's embedding function on the prompt input. Inside prompt embedding, select the embedding key from the response dictionary. Next, we can create VectorDB to load the conversations database. In results, we can use ChromaDB's query function on ChromaDB to retrieve the most relevant embeddings to our prompt embedding. Then create best embedding to store the embedded text from result. For the last line in the function, we can return best embedding. Above the call to stream response in the while true loop, create context to store the results from calling the new function after a prompt input. Inside prompt, we can reconstruct our prompt string with the context from our embedding. Save the program, and now your assistant will retrieve the best embedding from your vector database after each prompt and add it to the prompt for context. At this state, we have a basic RAG agent that works great for testing out Ollama RAG, but we want this program to have reliable long-term storage of our conversations and not just create a vector database from a Python list. For the long-term storage of our conversations, we will implement Postgres as our open source SQL database that we can use to create the vector database from upon starting our Python program. For those that have never heard of SQL, it stands for Structured Query Language. Postgres is the SQL language that we will be using to create, store, and retrieve our data in a highly efficient manner. This is the same database language used by big tech to store all of your data on their hard drives. Instead of relying on them to set up SQL databases, today we're going to set up our own. Your computer's operating system will determine which setup steps you should use for setting up Postgres on your PC. These are the steps to install Postgres for each operating system, so feel free to pause the video here while you get that installed. Let's now create a super user, aka admin, for our database. Start up your Postgres shell where we can write SQL commands with this command on Mac and Windows, or simply typing psql on Linux. Inside your SQL shell, write create user, the username you want to have, with password, putting your password inside of a string, and specify super user at the end. Now we can run this command to create the SQL database named memory_agent. We can run another SQL command to grant all privileges on the schema named public to our username. And next, grant all privileges on database memory agent to your user. We can then connect to our database by typing \c memory agent. We can now run this create table command specifying conversations as the name of the table. Inside of the table parameters, we will set the ID column to be serial primary key. We can set up a timestamp column that we will use to track the time we store a message in the table. We'll set our prompt column to equal text that is not null, meaning it must not be empty for every row. As the response column, it will also be text not null. Press enter to run this command, and we now have a table inside of our SQL database to store every message and response we have with our assistant. Now we can use SQL insert statements to add our 3 examples from the message history list to our Postgres table. Once the insert statements have been ran, your computer has a Postgres database set up to store your conversations. You can now exit out of the Postgres shell by typing \Q and pressing enter. Let's delete the message history list and load the messages from the database in our code. We'll start by importing these 2 libraries to interact with the Postgres database from our Python code. Then inside a variable named dbparams, we can specify the parameters for connecting to our database from the Python code. Set the user and password parameter to your actual credentials set in the previous steps. Define a new function named connectDB with the first line being a variable named con. This variable will call the PSYCOPG connect function, passing your database parameters. Once the database connection has been established, we can return con from this function. Now define another function named fetchConversations, which sets con to call the new connectDB function. With the results of calling the database connections cursor function as cursor, we can run an SQL select command to retrieve all rows from our conversations table. Inside a variable named conversations, we can store the results from the SQL command using the fetch all function. Now we can close our database connection and return conversations from the function. This will be a list in the same format as the message history list we were previously using to generate our embeddings. Above the line calling our create vector DB function, we will create a new variable named conversations to equal the results of calling our new fetch conversations function. And now pass the conversations list retrieved from our SQL database to the create vector DB function. Now that our program can retrieve from the SQL database, let's set up the program to store the prompt responses with our assistant in our new SQL database after each response is generated. Define store conversation that takes prompt and response as input parameters. First, connect to your Postgres database, and then with the connections cursor's function as cursor, execute an insert command that will be formatted with the inputs to the function within the insert statement to the database. Now call the connections commit function to effectively save all of the changes to our database. Outside of the with statement, we can now close the database connection. Then inside of our stream response function on the second to last line, we will call store conversation. At this point, we have a RAG agent capable of storing every conversation we have with the assistant and retrieving the single most relevant embedding to our prompts every time we send one. This is a basic implementation of RAG memory, but let's add more code to the agent to create a much more logical retrieval system capable of pulling context from multiple topics within your database. We first need to give our agent a system message to instruct it on how to properly use the attached context. Then we can add the system message formatted for the Ollama API inside of our convo list. Now define a new function called create queries that takes prompt as input. We will use this function to generate a list of queries to send to our vector embedding database. By using the LLM to create a list of queries to search for context on each topic it thinks it needs context on, we can then retrieve multiple needles in the haystack rather than just finding the embedding most relevant to our prompt. In the cases where our agent needs context that is not the most relevant embedding to our prompt, we'll need it to create these queries so that it can find the specific data that it needs. Sometimes our prompts will not even explicitly state what data we are going to need the agent to respond with, but the LLM can decide what it needs to properly respond. Inside our new function, create a variable called query message that will be the system message we use for this conversation for generating our retrieval queries. Now we could just add our prompt to the convo and generate a response here, but because I am using Llama 3 8B, it's commonly going to fail at responding responding in the proper format, which is going to be a Python list. And if it is not a proper Python list, the entire program is going to fail. In a previous video, I showed the common solution for this problem, which is fine-tuning a language model for this specific task. If you want to see that video, click the link in the top corner. For those of you not looking to dive into fine-tuning a model yet, we can use another technique to teach the small language model to respond correctly. Instead of going through the lengthy process of fine-tuning a language model, we'll teach the language model how to respond reliably in the correct format by using a technique known as multi-shot learning. Multi-shot learning is a language model technique where we manually add not only a system message, but prompts and responses to our conversation to show the language model how we expect it to respond. After we add a few prompt responses to query convo, we can add the prompt as the last message in the conversation, create response to call the Ollama chat function, passing the query convo to messages. We can then print the generated response to give us visual confirmation of what the agent is running queries on while we wait for it to generate the final response. When we receive this list from the LLM, it is going to be in the form of a Python string. But to use this in our program, we need to convert it to an actual Python list that we can loop through and send the queries individually to the vector database. We can do this by importing the AST library. Inside a try statement, we will use that library to convert the string variable into our Python list. If the response was generated correctly from the LLM, it will return the generated Python list. If the response is not in correct Python list syntax, an error message will be thrown, in which case we will return the prompt inside of a list for the embedding query. With the program now capable of creating a list of queries for our vector database, let's have our agent retrieve the two most relevant embeddings for each query and then run a prompt on each retrieved embedding to classify whether it is actually content satisfying the query. We can modify retrieve embeddings to take queries as input instead of prompt. Also add results per query. This parameter being set as 2 will make our program pull the two most relevant embeddings per query inside the queries list. Considering we will have this program run a prompt for each retrieved embedding to classify its relevancy, higher numbers will allow the agent to check more embeddings for context at the expense of directly increasing the agent's response time. So note that this important parameter is something worth experimenting with, even though I am setting it at 2 to see what best serves your needs. Then create embeddings as an empty set. For query and queries, copy in response to our loop and change prompt to equal query. As query embedding, select the response embedding. Copy the vector db variable into your loop, and as results, call the query function on vector db. Put query embeddings inside a list as an input parameter and set in results to results per query. As best embeddings, select the 0 index on results documents. Now we need a classify embeddings function to take the LLM generated query and the retrieved context to respond yes if the context is directly related to the query or no if it is irrelevant. As classify message, we'll create the system message for this conversation. In the classify convo list, we will again use multi-shot learning to teach the LLM to not explain the outputs. We only want the LLM to generate one token as its output to keep latency as low as possible for our agent. In response, call the Ollama chat function on the classify convo. For the last line in the function, return the message content after being processed by Python's built-in strip and lower functions. Back inside of the retrieve embeddings function, we can loop through best embeddings, checking that best is not already in embeddings, and if so, we can run the classify embeddings function to see if it returns yes, and then the program should add best to our embedding set. After the for loop's complete, we can return the embedding set. Define another function called recall to take prompt as input that we will use to call the create queries and retrieve embeddings functions to add relevant context to our prompts. As queries, store the response from calling create queries on our prompt. As embeddings, call retrieve embeddings on on queries. Now we can append the prompt constructed with the relevant embeddings for context to our agent's convo list, and then print a message telling us how many embeddings were added for context. With the recall function complete, we can remove the first line in stream response and replace these two lines in the while true loop to call our recall function on prompt. Lastly, delete this line that prints fetch conversations. At this point, we have an AI agent that stores and logically retrieves any message we have with our assistant, but we can definitely afford to improve the user experience of this program by adding a few features to our agent. Let's first add a loading bar to our program to visually show us the retrieval process, so we don't have to sit without feedback while the agent creates and processes the queries, which leaves us guessing when the response will start streaming. To do this, we will import the tqdm function from the tqdm library. Inside of the retrieve embeddings function, we will change the first for loop to use tqdm to create our loading bar. This will make our loading bar track progress based on each query being one step. The next feature we will add to make our agent have a better user experience is making our program recall memories only when we start out our prompts with a /recall command. Though we want this agent to store every message for future context, using the recall function when we do not need it to will dramatically increase response time unnecessarily. Delete the line calling recall in the while true loop, and then check if the first 7 letters of prompt equals /recall. If so, we can slice the first 8 characters off of our prompt, send the prompt to recall, then stream response. Else /recall isn't in the prompt, so we can append the prompt to convo, then stream the response without adding any vector embedding context. With our /recall command now working, let's add a /forget command. When our LLM creates a dog shit response, we can keep our AI from memorizing shit responses in its database. For this command, define a new function called remove last conversation to run this delete statement on the Postgres database. After checking if /recall is in our prompt, check else if the first 7 characters are /forget. If so, call remove last conversation, remove the last response and prompt from our convo, and print a line break. The last / command we will add for our agent is /memorize. This command will allow us to store our prompts without generating a response to attach to the vector embedding. Check else if the first 9 characters equals /memorize, then slice the first 10 characters off of prompt, and call the store conversation on prompt and response as memory stored. The last feature we will add to this Python program is colorizing all of our print statements. From the Ollama library, import the for class. On line 61, we can add to our print statement to set our assistant's responses as light green. On line 130, we will set our system messages to yellow. And on line 168, we will set our own prompts to white. Now you've built a local AI agent to store and recall any conversation you have with a clean interface built in Python. As you can imagine, there is countless things you can add to this code to improve upon and make your agent even more powerful. Leave a comment below letting us know what features you add to your agent. This has been AI Austin. I will see you in the next one.